Okay, let's think about infinity for a second. It's pretty mind-boggling that numbers just keep going, right?
Absolutely. Forever and ever.
But what if, and this is the kicker, what if some infinities are actually, well, bigger than others?
Ah, now you're getting into some really interesting territory.
Yeah, so today we're diving deep into a landmark piece of mathematical thinking. It's from 1874.
Georg Cantor.
Exactly. Georg Cantor tackled this idea of different sizes of infinity, and found something pretty astonishing.
That's right. We're looking at his paper. The title's a bit of a mouthful in German. Über eine Eigenschaft des Inbegriffes aller reellen algebraischen Zahlen.
Okay, let's maybe not try that one again, but what's the essence?
Well, in essence, Cantor was asking, how does the infinity of real algebraic numbers stack up against the infinity of all real numbers?
Real algebraic numbers.
Hmm.
Okay, let's unpack that a bit. Sounds pretty technical. What are we actually talking about there?
Okay, think of any real number that can be the answer, the root to a polynomial equation, where all the numbers multiplying the variables, the coefficients, are just plain integers, whole numbers.
Right, like x squared minus 2 equals 0. The answer is the square root of 2.
Exactly, that's an algebraic number. The equation looks like oval plus a euro plus all the way down to a0 as 20 by 8, 20 by 99 equals 0.
Gotcha. So n is a positive whole number. The a's are integers, a is in 0, and you said something about it being irreducible.
Yeah, basically meaning you can't simplify the polynomial further using just integer coefficients. And no common factors among the coefficients. It's the simplest form.
Okay, so square root of 2 works. What about like a simple fraction, 2/3?
Yep, 2/3 works too. It's the root of 3w minus 2 equals 0, see? Integer
Yeah.
coefficients.
Oh, okay. So lots of familiar numbers are actually algebraic numbers.
Many of them are. So Cantor's big question was about the whole set of them, all of them together. Our mission today is to explore how he proved something really quite surprising about this set and what that discovery actually meant for numbers that aren't algebraic.
Right, because my first thought, my gut feeling is, well, there's an infinite number of these algebraic numbers, right? So surely there must be just as many of them as there are real numbers in total. Feels like infinity versus infinity should be the same.
That's a very natural intuition. It feels like they should match up. But this is where Cantor did something really quite revolutionary. He showed that you can actually make a list, an ordered sequence.
A list.
Yes, a list that contains every single real algebraic number, which means, in mathematical terms, the set is infinite, sure, but it's countably infinite. The whole numbers 1, 2, 3.
Hang on, you can list all of them? That sounds impossible. How on earth did he manage that? There seem to be so many.
He came up with this really ingenious classification system.
Yeah.
He defined something called the height of an algebraic number.
The height.
Yeah, the height. So for our algebraic number w that solves that polynomial equation, a euro plus 0, its height, which Cantor called n, is calculated like this. N equals n minus 1 plus the absolute value of AO plus the absolute value of AO, and so on for all the coefficients.
Okay, wait. So n is the degree, the highest power in the polynomial,
Right.
and the a's are the integer coefficients. So you take the degree minus 1 and add up the absolute values, just the positive size of all the coefficients.
Exactly. So the height, n, sort of measures the complexity of the polynomial defining the number. Higher degree or bigger coefficients mean a larger height.
Okay, I think I follow that calculation, but how does that help list them?
Here's the crucial part. For any specific positive integer value of n, say n1 or n5 or n100, there is only a finite number of real algebraic numbers that have that exact height.
Only a finite number for each height, really.
Really. Cantor himself pointed out, for height n1, there's actually only one algebraic number, 0. For n2, there are 2, 1 and notable 1. For n3, he found there are 4, 2 noted 2, 12, and noted 12. The number grows, sure, but for any specific n, it's always a finite count. Let's call the count n.
Okay, that's the key then. Finite groups for each height level. So how did he use that to order all of them?
Simple, really, once you have the height concept. He said, okay, let's take all the numbers with height n1, there's only a finite number, one of them, list them in increasing numerical order.
Right, just 0 in that case.
Then find all the numbers with height n2, there's a finite number, 2 after 2, list those in increasing order right after the n1 number, so negative 1, then 1.
Okay, so after 0 comes -1, then 1.
Then you do the same for n3. Find all 3, 4 numbers, order them numerically, and tack them onto the end of the list. So after 1 comes -2, then -12, then 12, then 2.
And you just keep going, n4, n5, forever.
Exactly. You systematically work your way up through the heights. For each height n, you find the finite set of algebraic numbers, sort them from smallest to largest, and append them to your growing list.
Wow, so this creates one single infinitely long list, Wado-Diros and so on, that is guaranteed to eventually contain every single real algebraic number, and each one appears only once in a specific spot.
Precisely. As Cantor put it, every real algebraic number finds its definite place in this sequence based on its index. It's, uh, it's quite counterintuitive when you first hear it. This seemingly overwhelming infinity of numbers can be neatly lined up.
Yeah, my intuition is definitely taking a hit here.
I know.
Okay, so that's amazing in itself. But you said this was just part one. He used this ordering to prove something even bigger about all real numbers.
He did. This was the setup for his next major insight. He used this countability of algebraic numbers to prove that the set of all real numbers, even within a tiny little interval on the number line, is fundamentally more numerous. It's an uncountable set.
Uncountable, meaning you cannot make a list like the one he made for algebraic numbers, no matter how you try.
Exactly. You can't put them in a one-to-one correspondence with the counting numbers 1, 2, 3.
Okay, so how do you prove that? It seems even harder. You have to show that any attempt to list all real numbers is doomed to fail.
That's the logic, yes.
Yeah.
He used a proof by contradiction, a really elegant one. He said, okay, let's pretend for a moment that you can list all real numbers. Let's say you give me any infinite list of distinct real numbers, call them 1 prime, 1 euro, prime, and so on.
Okay, so we're assuming this list contains every real number.
We're assuming that for the sake of argument. Now, Cantor showed that no matter what interval you pick on the number line, say from A to A, where A is less than other,
Yeah.
he can always find a real number inside that interval, which is definitely not on your supposed complete list.
Always. How does he find this missing number?
Through a clever process of constructing nested intervals, intervals inside intervals, getting smaller and smaller. You start with your chosen interval, let's call it A. You look down your list, weight, ALA, and find the first two numbers from that list that fall strictly inside. 8A. Not the endpoints, but inside.
Okay, find the first two list members within the interval.
Let's call them AL prime and AL prime, and let's say A prime is the smaller one. These two numbers define a new, smaller interval, A pop prime, which is completely contained within an AO.
Right, so you've zoomed in, and this new interval definitely contains at least those two numbers from your list.
Well, it contains them, but we're actually going to use them to define the boundaries of the next step. Now we repeat the process. Look further down the list, A about prime, for the first two numbers that fall strictly inside this new interval, A at prime.
Okay, find the next two members inside the smaller interval.
Call them A double prime and A double prime, with A at double prime smaller. They define an even smaller interval, AL at double prime. And you keep doing this. You generate a sequence of intervals, each one nested inside the previous one, and so on.
I can picture them shrinking down, like Russian dolls. But how does this show the list is incomplete?
Well, there are two possibilities for this shrinking process. Possibility one, maybe it stops. Maybe after some number of steps, say you create the interval, you find that there's at most one number from your entire infinite list, W prime, left inside this interval.
Okay, so it gets so small it contains only one or maybe zero numbers from the list.
If that happens, then you can just pick any other real number, call it Grau, that's inside this final interval, but isn't an endpoint.
Yeah.
That number cannot have been on your original list, W prime, because we know at most one list member is in there, and maybe gray isn't it, or maybe there are none. So boom, you found a real number missed by the list.
Ah, okay. That makes sense. If the process stops, the label was incomplete. What if it doesn't stop? What if you can keep finding two numbers and making smaller intervals forever?
That's a possibility too. An infinite sequence of nested intervals. Now think about the left-hand endpoints, AKA, AKA, AP, double prime, and so on. This is a sequence of numbers that's increasing or staying the same, but it can never get bigger than the original right endpoint.
Right, it's bounded above.
Exactly. And a fundamental property of real numbers is that any non-decreasing sequence that's bounded above must converge to a limit. Let's call that limit or infinity. Similarly, the right-hand endpoints, AK prime, A double prime. It's a non-increasing sequence bounded below by A, so it must also converge to a limit. Let's call it APPA.
So we get these two limit points, A, Fe, and Ve, squeezed out by the infinite sequence of intervals. What about them?
Now, Cantor looked at the relationship between Heve, case 1. They might be equal, AFib might be exactly the same number as Beofe. Let's call this single limit point A.
Okay, they converge to the same single point.
Now, could this point of view be on our original list? W prime.
Hmm. Well, to make each new interval, we picked two numbers from the list inside the previous one to be the boundaries. Almost feels like Ga should be trapped between numbers from the list.
Think about how we picked Aga and so on. We always pick the first two available numbers from the list, WS, inside the current interval. If E was on the list, say it was mu k prime, then eventually, as the intervals shrink, E gama God would have to be chosen as one of the endpoints, like Akai, to define a smaller interval. But the next interval would be defined by numbers strictly inside. So I would be excluded from all subsequent intervals. It can't be inside all of them if it was used as a boundary partway through.
Ah, right. By definition, the limit point lies within all the intervals, arbitrarily far down the sequence. But if it were on the list, it would eventually define an interval boundary and thus be excluded from later intervals in the sequence. So E cannot be on the list W prime.
Precisely. It's a subtle but crucial point. So if Aga got asked, then E is a real number not on our list.
Okay, what's the other case for the limits?
The other case is that honor is strictly less than honor. They don't converge to the same point. They define a limiting interval, possibly just a single point if they were equal, but here it's a definite interval.
Okay.
In this case, any real number you pick within the close interval, honor must lie within all the nested intervals, for all n. And for the exact same reason as before, because the endpoints honor were always chosen from the list prime, and the next interval was strictly inside any number in this final limiting interval, honor cannot be on the list prime.
So whether the process stops or goes on forever, and whether the limits are equal or define an interval, you always find a real number within your starting interval that was not on the supposedly complete list of U prime.
Exactly. The inescapable conclusion is that no such complete list can exist. Any attempt to list all real numbers will inevitably miss some. Therefore, the set of all real numbers is uncountable.
Wow. Okay. So algebraic numbers, countable. Real numbers, uncountable. And that difference leads directly to...
transcendental numbers.
Right. Because if you take all the real numbers, uncountable, and you remove all the algebraic numbers, which we now know are countable, you're still left with, well, most of them.
You're left with an uncountable number of them, in fact. These leftovers, the real numbers that are not algebraic, are precisely what we call transcendental numbers. They are not the root of any polynomial equation with integer coefficients.
So Cantor didn't just prove they exist, he proved there are, in a sense, more transcendental numbers than algebraic ones.
Infinitely more, yes. And because his proof works for any starting interval, no matter how small, it means that in every tiny slice of the number line, however small you make it, there are not only algebraic numbers, but also an infinite, uncountable number of transcendental numbers packed in there.
That's incredible. They're not just rare curiosities, they're everywhere, densely packed.
Absolutely everywhere. It's a profound realization about the structure of the real number line.
And this was an existence proof, right? He showed they must exist because of the countability difference, but his proof itself didn't spit out, say, pi or e.
Correct. It was non-constructive. It proved existence based on set sizes. He did mention in the paper that his method provided a new proof for their existence, acknowledging that Louville had earlier given a constructive proof, actually building specific examples of numbers and proving they were transcendental. But Cantor's approach was more general and powerful in showing their sheer abundance.
So what was the fallout from this? Did it, break mathematics?
It didn't break it, but it certainly shook it up and reshaped it fundamentally. This work on countability, uncountability, and different sizes of infinity was revolutionary. It laid the very foundations for modern set theory.
Set theory, okay.
Which is now, foundational to almost all branches of mathematics. Cantor himself stressed the difference between what he called a continuum, like the real numbers in an interval, which is uncountable, and a totality or aggregate, like the set of all real algebraic numbers, which is countable. Understanding that distinction, that the continuum cannot be mapped one-to-one onto the integers, was key.
Okay, let me try and summarize this because, wow, Cantor figured out a way to order all the real algebraic numbers using their height, proving they are infinite but countable.
Yep, like the integers 1, 2, 3.
Then he used this incredibly clever nested interval argument to show that no matter how you try, you cannot list all the real numbers. They are uncountable.
A bigger kind of infinity.
And because the real numbers are uncountable but the algebraic subset is countable, the numbers left over the transcendental numbers must also exist and be uncountable, and they exist in every interval.
You've got it. That's the core logical flow of this 1874 masterpiece. It revealed these different sizes of infinity and the surprising density of transcendental numbers.
It really turns your intuition about infinity upside down. The idea that some infinities are just fundamentally larger than others is still hard to fully grasp.
It really is. It's one of those mathematical ideas that takes time to sink in, and even then it retains a sense of wonder, I think.
This has been, yeah, absolutely fascinating. Really makes you think differently about the number line itself.
It does. And maybe here's a final thought for you, something to chew on. Think about other big infinite sets, like maybe the set of all possible computer programs, or the set of all points in a 2D plane. Are those sets countable like the algebraic numbers, or are they uncountable like the real numbers? What kind of arguments, maybe inspired by Cantor, could you even use to try and figure that out? Exploring those kinds of questions is where you really start to see the long-lasting impact of Cantor's journey into the infinite.